Okay, this is chapter 8, third lecture related to confidence interval. Before, what we used to do, we used to take a sample and we calculate their sample mean, whatever we get, and then we calculate standard deviation of that sample mean, and we were trying to estimate population mean. Like what we were doing, if we take a sample of CIP class, like let's say statistics class, and we want to say what is their height, and we want to estimate the average height of all CIP students. So x bar will be average height of, let's say, CIP mathematics class, and mu is the average height of all CIP students. We don't want to calculate the height of all CIP students. We just take one sample, we calculate their sample height, and we try to estimate our population height, which is our all CIP students. So before we were estimating this mu, but now we want to build a interval, because this mu is only a one number, but we are not sure that is it correct or not, because it is based on one sample. But now we will construct an interval. So confidence interval of the population mean mu, we will develop this confidence interval, and there are two important things which we need to take into account. The one is either standard deviation is known or standard deviation is unknown. When standard deviation is known, we will use z formula, and when standard deviation sigma is unknown, then we will use t distribution. We will discuss it later. So for the time being, we are still using z distribution, which you are using so far. So we will construct confidence interval for population proportion as well. As you have seen in your last topic, we were constructing we were estimating population proportion as well on the basis of sample proportion. So here you can see this is the point estimation. Point estimation means on the basis of x bar we were estimating mu, population mean. That is the point estimation. But now we are not getting only one number, we will get an interval, lower confidence interval. Here we will get a lower value, and here we will get an upper value, and we will say that the population mean will lie between these two numbers, so it is more reliable as compared to point estimation. Okay, this is called population mean, and this is called sample mean, which you already know. This is called population proportion, and this is called sample proportion. So these are just notation to get familiar. Okay, so confidence interval tells us how much uncertainty is associated with point estimate of population parameter, and interval estimates provide more information about population characteristics than does a point estimation. This point is exactly the same which I am explaining, that this mu is only one number. This is only one number. We are not sure that either this is a correct population mean on the basis of one sample or it is varying. So we develop an interval. Let's say 70 to 90. We can say that okay, population mean may lie between these two numbers, so it is more reliable because we have a variation, but in this case we have only one number. So that was the concept. So taking into consideration the variation in the sample statistics from sample to sample based on observation from one sample, so these are the integral parts of confidence interval, and interval gives us the range of values. So we always develop confidence interval on the basis of 95%, 99%, or maybe 90%. We can never construct a confidence interval of 100%, because we can never be 100% confident. If we are 100% confident, we don't need to do all these statistical applications. So we always keep the margin of error. If we say 95% confident, so it means we are not confident 5%. If we say we are 90% confident, it means that we are not 10%, we are not 10% confident. So this is called margin of error, and in statistics we denote it by alpha, level of significance. So we take one example. and you will get a clear idea that what we are doing. Let's say a population mean is 368 and population standard deviation is 15. We take a sample of 25 and we know that population mean is 368, and this is how we develop the confidence interval, which we used to do z alpha by 2 sigma over square root of n. I will explain this alpha by 2 later. What is this alpha by 2? So mu is 368, z alpha by 2 for 95% confidence interval. For 95% confidence interval, z alpha by 2 is 1.96. I will explain this later as well so that you can easily calculate it. And 15 standard deviation is given, sample size is 25, it is already given. So you can see that this is an interval which tells us that the population mean will lie between this and this number. Although this is an example and we know what is population mean. Population mean is 368 and you can see 368 lies within this interval. Okay, that was an example. In reality, we will not be given this mu. We will not be given this mu, and we will try to estimate this mu on the basis of our sample, and we will calculate sample mean. So let's see, when you don't know mu, you use x bar to estimate this mu. So we take a sample of 25, we take a sample of 25, we are given sigma 15. From this sample we calculate their sample mean. So we calculate their sample mean and let's say it's 362.3. So the formula will become x bar plus minus z alpha by 2 sigma square root of n. Here we will substitute our sample mean 362.3 plus minus 1.96, which is from z table, 15 over 25, and when you develop this interval you will get this confidence interval, and you can see our population mean is lying, this is 368 and it lies within this interval. Since this mu is between this and this interval, based on this sample makes a correct statement about population mean. Okay, so you can take different samples. For sample 1, our sample mean was 368. When we developed its confidence interval, it is 356 and 368, and you can see our population mean, which is 368, is well between these two numbers, so it is a correct estimation. Yes, we take a second sample, its sample mean is 369, and again our 368 lies within this interval, so it is also a correct estimation. Okay, further we take a third sample. Now third sample is giving us a wrong estimation, 368 does not lie within this interval. Fourth and fifth also say yes. So you can see if you draw 5 samples, 4 times we are getting a correct estimation, so which assures us that if you take any sample you should be more than 90% confident that you are estimating a true population mean. Okay, in practice you only take one sample of size n, and could be any, let's say 30. In practice you do not know mu. Of course we do not know mu, we are trying to estimate mu. You do not know if the interval actually contain mu or not. Of course we are not sure. However, you do know that 95% of the interval formed in this manner will contain mu. If we construct 90% confident, it means we are 90% sure that this mu will lie within this interval. Thus, based on one sample you actually selected, you can be 95% confident your interval will contain mu. Normally in statistics we construct 95, 90 or sometimes 99%. Okay, so this is a simple figure, I don't need to explain it, I already explained it. So the general formula for all confidence interval is this: point estimation is called mu x bar plus minus critical value. If we are applying z table, z test, it will be z alpha by 2, and standard error. sigma over square root of n. So that is the general form of the formula. You will see later on all the formulas will be constructed on the basis of this explanation. As I said, we can never be 100% confident, so the percentage will always be less than 90%. You can say I am 99% confident, you can say I am 90% confident, you can say I am 95% confident. But if you go beyond 90%, then or less than 90%, then we don't need to apply these tests, because statisticians suggest that 85% or 89%, if your margin of error is more than 10%, if your margin of error is more than 10%, it means you don't need to take any decision regarding that sample. Suppose confidence interval, now here we develop a confidence interval. Suppose confidence level 95% are also written in 1 minus alpha form. I have already explained this thing. I explain it in simple words. If you are saying that 95% confidence interval, so it means that we are not sure 5% alpha will be 5%, which is margin of error, which is very important in every example. If you say I am constructing 90% confidence interval, it means that your margin of error is 10%, total is 100%, total is 100%. If you are constructing 99% confidence interval, it means your alpha is 1%. Okay, we develop confidence interval. There are two forms. We know population mean, and then we know standard deviation, population standard deviation. We use z-test. If we know, we develop confidence interval, and we know population mean, and we are unknown about population standard deviation, then we use t-test. Otherwise, we use population proportion, and we will explain it later. There are some other identifications which tells us that either we are using population proportion or what. Okay, so this is the formula. I have already explained this formula to you. Population standard deviation sigma when known. This is very important thing. You must be sure either you are given population standard deviation or not. This sigma is population standard deviation. Okay, sigma means population standard deviation. If you are known with this, then we will apply x bar plus minus z alpha by 2. Then we will use z formula, then we will use z if we know population standard deviation. This is very important statement. Okay, now as I said, for 95% confidence interval, how do we know z alpha by 2 is 1.96? 95%, it means this is acceptance area. This is acceptance area. So margin of error is 5%, will divide into two portions, 2.5% here and 2.5% here. 2.5%, which is alpha by 2, 0.025. So from minus infinity to 0.025, if in the z table you see where is 0.025 or closer to it, you will find here minus 1.9, here you will find 0.06. so z alpha by 2 is minus 1.96. since it is symmetrically distributed, we did these examples in previous topics, so it would be here plus 1.96. so that is why for 95% z alpha by 2 is plus minus 1.96. in examples I will solve for 90%, how do we calculate it, but you don't need to do this. So these three are quite famous. We in whole book we will use these three, but you should know how do we calculate z alpha by 2 other than 90, 95% and 99%. I may ask it in the exam, but in exercises you can directly write, okay, 90% confidence interval, z alpha by 2 is 1.64, z alpha by 2 is 1.64. okay, for 95% z alpha by 2 is 1.96. you can directly use it, you don't need to calculate it other if you are not asked to calculate it. So we solve one example. A sample of 11 circuits from a large normal population has mean resistance of 2.2 ohms. A sample of 11 circuits. We take a sample of 11 circuits from a large normal population has mean resistance 2.2 ohms. We know from past testing that population standard deviation is 0.35, right? So it means that x bar is 2.2 because this from mean is coming from 11. Determine 95% confidence interval. For 95% confidence interval, as I said, z alpha by 2 is 1.96. You don't need to calculate it, as we already know from the table. You don't need to calculate it if you are not asked. If it is, I'm repeating my words, if it is 90%, 95% or 99%, you don't need to calculate z alpha by 2. You can directly write it is 1.64, it is 1.96, and it is 2.56 something. So that is why we are directly writing z alpha by 2 1.96 for 95%. So you can simply substitute the values. This is the formula. You can simply substitute the values. X bar is given 2.2, z alpha by 2 1.96, sigma is 0.35, n is 11. So this is the interval which we need to construct. What is its interpretation? We are 95% confident that the true mean resistance is between these two numbers. Although the true mean may or may not be in this interval, but in this manner, the way we did it, we are 95% confident that it will lie within this. So again, I'm repeating this figure. I already did this. Population mean, if sigma is known, z test. If sigma is unknown, then t test. This is very important thing. I will keep explaining it later on.